Today we're going to switch gears and start talking about a different kind of prediction. This is time series forecasting. A time series is an observation of a variable, for example, sales, or a reading from a sensor over time. And unlike regression, in which you're trying to predict one variable using another set of variables, you're only looking at a single variable, or at least in our case, we're only looking at a single variable, and we're trying to predict its future values based on its history. Let's start with an example and introduce a little bit of notation here. Let's suppose each week we observe the sales, let's suppose at a retail outlet, and let's suppose we've done that for maybe the past couple of years. And here I'm showing a little bit of a spreadsheet that shows the first 14 weeks and the sales that were observed for each of those weeks. We're going to call the values, the sales that we observed, Z, and we're going to put a subscript on there, T, denoting the week in which that observation was made. So in this example, Z sub 1 would be 100, the sales for week 1. Z sub 2 would be 108, Z3 would be 114, and so forth. And the first step in analyzing any time series is to plot it over time. And the things you would be looking for would be, is there a trend in the data? Are there seasonal patterns in the data? Are there outliers in the data? And that will help guide us in what we do, what kind of model we use to do the forecasting. The problem in forecasting is pretty easy to state. Let's suppose we've observed 100 weeks worth of data, and we'd like to predict what's going to happen in week 101 and 102 and 103 and 104 and so forth. The most complicated part of it is understanding the terminology. So I'm going to have to walk you through the terminology, and you're going to have to struggle just a little bit, but it will eventually make sense, and it will give you an advantage in understanding time series forecasting techniques. So first of all, if I'm talking about a forecast of Z, rather than saying Z, I'm going to put a hat on top of it, that little symbol there, and that means that the value we're talking about is a forecast, not an actual value that we've observed yet. And then we have to talk about the number of periods into the future that we're forecasting. Are we forecasting 1 or 2 or 3 or 4 periods into the future? And we denote that by a number that we put in parentheses following the forecast value notation. And L is used to denote the number of periods into the future that we are forecasting. And then finally, we have to denote the time at which we are making the forecast. What data do we have available when we're making the forecast? And that is denoted by the subscript T. So typically you will have observed data up until time T, and then you're making forecasts for time T plus 1, T plus 2, and so forth. So a particular one of those forecasts will be denoted by the value of T and the value of L that you use. Okay, to check your understanding, you should be able to look at an expression such as this and say, well, this is a forecast, and I know when the forecast was made, and I know for what period the forecast is. So make sure that you understand that. Okay, the hat on the expression means this is a forecast. The 50, as the subscript says, this is the forecast we're making at time 50. Normally that means the end of period 50, after we have observed the demand for period 50. And the 5 in parentheses says we're forecasting 5 periods into the future. So that expression denotes the forecast of Z55, or the demand, this is a demand time series, that we made at the end of week 50. The most simple model that you can come up with, but a model that's used quite often and works quite well in some circumstances, is called the random walk model. We'll talk a little bit later why that is the terminology used. It's also called the naive model, and it also has another fancy name there that we're not even going to talk about yet. But here's the way the model works. At the end of week 1, I've observed sales of 100. And you say, what would be my forecast of sales for week 2? Well, 100, what we just observed. What would be the forecast that I make in week 1 for sales of week 3, or week 4, or week 5? Well, those are also 100. That's the best guess I can come up with. And then we move forward into week 2, and we observe sales of 108, and that becomes our new forecast for all of the future weeks. And then in week 3, the forecast changes to 114, and so forth. Mathematically, the way you say that is Z hat sub t, the forecast that you make in week t, let's suppose week t is 7, for L periods into the future, it's just Z sub t. So in week 7, the forecast that we make is 150, or the value of the sales for week 7. And that forecast is used for all future weeks until next week, week 8, when we update it. And the way we test our forecast model is by looking usually at the errors made for one period into the future. So we're going to denote by E sub t the one period forecast error made at time t. In other words, let's say at time 10, I observe what the actual value of the series was, and then I look at the forecast I made one period earlier, or at time 9, and the difference between the actual and the forecast is the error for that time period. So if you look over in the little spreadsheet there, you see that in time 2, I observed an actual of 108, but the forecast that I made one period earlier was 100, so I take the actual minus the forecast and get an 8. In period 3, the actual was 114, the forecast of one period earlier was 108, so the difference of 6 is the forecast error. And a little repetition doesn't hurt here. I'm walking you through it again. The error made at time 2 would be the actual minus the forecast made at time 1. So first, the actual is 108, as shown there. And the forecast that I made one period earlier is 100. And so we complete the arithmetic, and we see that the actual demand at time 2 exceeded the forecast made at time 1 by 8. A positive error means that we have under forecast, the actual exceeded the forecast. A negative error would mean that we had over forecasted. Okay, the first thing I would do is to plot the errors, or the residuals. So these points show the difference between what actually happened each week and the forecast that I made a week earlier. And I'll give you a couple pointers in interpreting these. You notice that there tend to be more points above 0 than there are below 0. And that simply reflects that, well, the data was trending upward, and if I'm always using last week's sales as a forecast of next week's sales, I'm going to tend to under forecast, and that's going to give me lots of positive errors when I take the actual minus the forecast of a week earlier. The other thing that you might notice is that week 60, there was a fairly large error. The actual sales exceeded the forecast made a week earlier by about 35. So that's probably an outlier that we would investigate and probably would find some special reason to explain that. In addition of plotting the errors or the residuals over time, I would also do the histogram. And the histogram shows me what I just pointed out before. The average is to the right of 0, or the center of the distribution is to the right of 0. And also, maybe there's an outlier up there at about 35 or somewhere in that region. We measure the quality of our forecast by computing a standard error, which is basically the standard deviation of the errors. And this is analogous to the standard error that we have in regression analysis. There's a formula given there, but I'm going to just walk you through the steps as to how we compute it. Let's pretend we have 100 weeks in our sample, and I'm only showing the last few here. But for each week, we take the difference between the actual and the forecast that was made in the previous week, and that's our error, and we're squaring each of those errors. Then you take the average of the squared errors, in this case overall 100 weeks, and that is sometimes called the mean squared error, and that's that number you see there, 112.7844. And then after you've squared all the errors and then taken the average of the squared errors, you take the square root of that number, and that is your standard error. In this case, it's 10.62. With our random walk example, let's pretend that we're now in time period 100 and we want to predict one period into the future. In other words, we're going to predict what's going to happen in time period 101. So the forecast is just the most recently observed value, that's 394, and we've already computed the standard error of 10.62. And that allows us to make a prediction as to the range of variation of numbers that we could see in time period 101. To get a predicted range of values that we will see in time period 101, we take the forecast, which is 394, and we subtract 3 standard errors, and that's our lower bound, and then we add 3 standard errors, and that is our upper bound. And if the actual value that occurs in period 101 falls outside that limit, our convention will be to consider this an indicator of a special cause, and if we were to check, we would probably find out that something unusual was going on during that period. And next we're going to talk about, suppose I'm using my random walk model to forecast more than one period into the future. How much confidence do I have in that forecast? Well, it turns out this is true only for the random walk model. There will be different formulas for other models that we will develop in the future. But for the random walk model, the standard error of the forecast for L periods into the future, which we will denote SE sub L, it is equal to the square root of L times the 1 week standard error. So now we're ready to talk about forecasting multiple periods into the future. So let's suppose we're at week 100 and we want to make a forecast of the demand 5 weeks into the future. In other words, the demand for, or the sales for week 105. First of all, we know the forecast. With the random walk model, it's just the most recently observed value, so that will be 394. And then next, we are going to compute the standard error of the 5 week forecast. So we take the square root of 5 times the standard error of the 1 week forecast, and we get 23.74, which is quite a bit larger than the standard error that we get when we're only forecasting 1 week into the future. And that makes sense. The farther into the future we're forecasting, the wider the range of variation we would expect. And then the predicted range of variation for Z105 is the forecast plus or minus 3 standard errors, and in this case we're talking about the standard error of the 5-week forecast. So what we would literally be saying is we're fairly confident that the actual demand for week 105 will fall somewhere between 323 and 465, and that's the statement that we make at the end of week 100 after we have just observed the demand for week 100.